All right, so let me write the topics on the board, the things we're going to discuss today, and then I'm going to start in a minute. All right, so what we're going to do is that we are continuing chapter 3. I'm going to quickly recap the method of image. We did one example, not complete, last Thursday. So I'm going to complete that one, and I'm going to give you one more example about method of image as well. We're going to look at the charge distribution, forces, and energy as well. Okay, so once we are done with method of images, I'm going to start separation of variables. Separation of variables, it's an important method. People use that for solving differential equations. I expect that you guys are somehow familiar with the whole topic, but this is one of those methods that is so much dependent on what problem you are applying it at. Okay, so I'm going to give you the basics of the separation of variables, how it works and why it works. It doesn't work all the time, but whenever this method works, it's amazing. Okay, it's amazing that how it works. And I'm going to give you one relatively long example in Cartesian coordinates. This is one of those methods. It's a mathematical method, and you learn it by doing example. And I teach them by doing example the same way that your textbook approaches that. Okay. So once we do that, then there are a couple of more examples for Cartesian coordinates. I'm going to do that next Tuesday, and also there's one very interesting method, one very interesting example for spherical coordinates. Okay, so this is what we're going to cover today. One reminder, we previously talked about this. The time of the midterm, October 29th, was tentative, okay? And I already told you the pace that we are moving forward. We are not going to have that on October 29th, which was actually today. The midterm will be after we finish chapter 3. So it's going to be, I anticipate it's going to be 2 or 3 weeks from now, okay? So chapter 3 is included in the midterm, and we're going to have that after we finish chapter 3. Sounds good? Okay, and your quizzes, I'm going through the quizzes. Okay, so this is the one that I really need to look at each of them. More or less, the grades were good. Okay, I was impressed. And your TA is working on assignments as well. Any question? No? Okay, so let's...
Sorry, I missed it. When is the midterm?
What's that?
Did you say when the midterm was?
The midterm is when we finish chapter 3. So I anticipate it's going to be 2 or 3 weeks from now.
Okay.
We have at least 1 more week to finish chapter 3.
Okay, gotcha.
So for now, don't worry much about the midterm. Just focus on the science here, and then I will tell you.
Sounds perfect.
Okay, we already talked about this, but a couple of students emailed me again, checking when is the midterm. So that's why I'm giving you a reminder of what we're going to do for that. Sounds good? Okay, so shall we go to the method of images? So you guys remember what was the general idea of the method of image we talked about it last Thursday? So this is useful when we have a conductor, okay? Or later on we will see that some insulators, depending on the dielectric constants, that could be useful too. But the idea is that if you have a conductor, you will have some induced charges. And if you are looking for the electric field and electric potential created near that conductor, it's useful to consider a separate setting where you don't have a conductor, but you have other charges, oppositely negative charges, okay? And that way you can create the electric potential and electric field that satisfies the boundary condition and Laplace's equation for the actual problem you're dealing with, okay? And we said the trick about the Laplace's equation is that if you can find any function that satisfies the Laplace's equation and satisfies the boundary condition, that is your solution. Okay, so if somehow you are smart enough, you can come up with a shortcut or anything like that. If you can come up with the answer, that is the answer. No one's going to tell you why you took this approach. Okay, so method of images is one of those type of shortcuts. And the example we did, we started but we didn't complete, was if you have an infinitely long conductor and imagine this is connected to Earth, so the electric potential right and the surface is 0, and then you put one electric charge, let's say Q, right on the top here. Okay, so what happens is that if Q is, let's say, is positive, okay, let's imagine it's positive, what happens is that negative charges are going to come and distributed on the surface. Okay, so this positive charge attracts negative charge. And we said the electric field lines, they're going to be something like this, always perpendicular to the conductor. Okay, come over here and then go to the point charge right on the top. Okay, so this is the type of electric field that we expect to get from this system. The question was calculating electric potential. So what is electric potential in everywhere in the space? And then from the electric potential, you can calculate electric field and almost every other quantity, okay? And the trick here was that instead of considering this Q and this conductor, we can consider a separate setting, okay, where we do not have any conductor. I'm just going to draw the dashed line here. Okay, imagine here you do not have a conductor, but you have one charge Q exactly where it was. Let's say the distance here is D. So you have the charge Q exactly on the same position, and then you have another charge negative Q on the other side. Okay, so you got positive Q here, you got negative Q here. And the point was that if we look at the potential created by these 2 point charges, that potential satisfies the boundary condition here as well. Okay, so what is the boundary condition here? The boundary condition, we have 2 conditions. And the first one is that V should be equal to 0 at the surface of this conductor, and I'm going to call that at Z equals 0. Okay, so this is one boundary condition. The other boundary condition is V should be 0 when we are far away from this point charge. So I'm going to say that at infinity, V should be 0. Okay, so if we go so far away, the potential should be 0. And these two are the boundary conditions for this system. Okay, and now if we look at the potential created by these 2 charges, okay, we will see that the potential created by these 2 charges satisfies both of these conditions. The second one is kind of obvious because you have 2 point charges. Of course, whenever you go so far away to infinity, the potential becomes 0. So this one is already checked. The first one, we should write the potential as a function of x, y, z, and then we can look at that, and you will see the potential becomes 0 on the surface where z is equal to 0. Okay, so this is a plane at z equals 0. Okay, we look at that potential. So v, x, y, z, I'm writing as a function of x, y, z coordinates. We have got 2 point charges here, so 1 over 4 pi epsilon 0. We will have two terms. The first term from Q is going to be Q over distance, and distance here is x2 plus y2 plus z minus d. Here we have z minus d because the charge Q is sitting at z equal to plus d. Okay, so this distance from the charge Q becomes x2, y2, z minus d to the power of 2 under square root. And the distance from the other charge, negative Q, here I want to put negative Q, is very similar. Instead of minus d, it's sitting at minus d, so it becomes positive. So x2 plus y2 plus z plus d to the power of 2. Okay, so this is the potential we have. We wrote it for 2-point charges. And now if you look at this, and if you put z equal to 0, you will see that these two terms cancel out each other. So v x, y, 0 becomes 0. And that's good because this satisfies the first boundary condition as well. So in summary, the potential created by these two charges, okay, satisfies every condition that we need for potential of 1-point charge near the conducting surface, okay? And of course, we can use this potential for the area above the conductor where it's empty. Inside the conductor, potential is just flat, 0, and there is no electric field. Okay, sounds good? So far it's clear? You guys following me?
I just have a small question. I just want to know where you get the C minus D. That's all.
Where did I get what?
The C minus D. I'm just having a hard time seeing it.
C minus D.
Yeah, I just want to know how.
Oh, Z minus D. Yes, of course. So the charge Q is sitting at Z equal positively, right? So if you want to look at the distance from this, okay, so you want to look at the position Z where you are at minus the position of the charge.
No.
Okay. So imagine this point here in space, okay, is X, Y, and Z. What is the distance between these two? That's technically the separation distance, okay? So technically if you want to write it in a complete way, you want to say X minus, let's say XQ, where the charge Q is sitting, to the power of 2 plus Y minus YQ. YQ is where the charge is sitting, plus Z minus ZQ, that is where the charge is sitting. Okay, so this is a very general form to find the distance, okay? But this charge, we assume that is sitting at Z plus D, and X and Y are 0, okay? So this becomes 0, this becomes 0, this ZQ is D. So combined, it becomes X2, Y2 plus Z minus D2.
Oh, okay, I see now. Thank you.
Make sense?
Yep.
Good. Let me find my eraser here. Okay, so the next thing we want to look at is the surface charge distribution of the induced charges. Okay, so we said the negative charges come over near the positive charge, and you can imagine if you are very close to this charge Q, you have a lot of negative charges, and if you move further and further away, right, the density of negative charges are going to drop as you move away. Okay, so the question here is that what is the density of the surface charges? And to find that, if you remember, we had the equation that sigma on the surface of the conductor is negative epsilon 0 dV over dN, and this is the derivative in the normal direction to the surface. here with the setting that we have, the assumption is that the z direction is normal to the surface. We can say sigma is negative epsilon 0 dv dz. And this needs to be calculated at z equals 0. Okay, so this derivative, I'm going to write that quick here, comes negative epsilon 0 times 1 over 4 pi epsilon 0. So what I'm doing is that I'm just taking derivative of this term, okay, and then I'm going to calculate that at z equals 0. Okay, so first the derivative becomes negative q z minus d over x2 y2 z minus d2 to the power of 3/2. And from the second term, we get q times z plus d over x2 y2 z plus d2 to the power of 3/2, all in bracket. Okay, so if we calculate this, the whole thing at z equals 0, it becomes a lot more simple, and sigma as a function of x and y becomes negative qd divided by 2 pi times x2 y2 d2 to the power of 3/2. Okay, so you get this one. The surface charge density of the induced charges, and we said, of course, it has to be, it needs to have a negative sign because induced charges have opposite charge with respect to Q. And then here we have x2, y2, x2 plus y2 are technically the distance from this point. Okay, so as you go further from this point, what happens is that the denominator increases, right? The denominator increases, and then you get less and less surface charges, and that's what we expected, right? The next part, what we wanted to look at was, what is the total density of induced charges here, okay? And in order to do that, we need to integrate it over the whole surface from where we have this charge Q all the way to infinity. Okay, so if you integrate the whole charges, right? If you integrate the whole charges, you can find the total amount of induced charges on the surface. Okay, so far so good. Any question you have so far? Is it clear, the concept, what we are following here?
So you derived the potential by simply adding the two Q's?
The potential I calculated by looking at the derivative of the so again, the question was the potential or the surface charge?
The surface charge, but I'm just asking.
So this is the surface charge, and I calculated based on the derivative of the potential with respect to z. Okay, so basically this is electric field, right? We are looking at the discontinuity of the electric field on the surface. And we already talked about that surface charge is proportional to the discontinuity of the electric field. And that's what's happening here. Okay, so far this part is very general for any conductor. Okay, this part. Okay, sigma is the derivative of the v with respect to n. Okay, and here in this case, n is normal to n is the direction normal to the surface, and that becomes dv over dz. Okay, so this is general. In order to calculate further, the v, I used this potential here. And I took derivative of the whole thing here with respect to z, and that becomes this long term. It looks complicated, but eventually it becomes simple because what we care about is the value of this derivative at z equal to 0. So all these z terms here became 0. Sounds good? All the z terms became 0, and this is at the end the surface charge density as a function of x and y. Okay, the rest are constant. Q is a constant, D is a constant, 2 pi, and D here is a constant. The density of the surface charges depends on how far you are from the projection of this charge on the surface. Okay. Did I answer your question?
And all of this by just taking another situation when there's a negative Q exactly at another distance?
Yes. So the whole potential, okay, the whole electric potential, we wrote it based on having two charges, Q and negative Q here. Okay. So the first thing was checking if this potential satisfies the boundary condition that we want for this problem. Okay. And if it does, we say, okay, the potential created in this situation is exactly the same as potential created by this situation. Right. So once you do that, then you can use just this electric potential for the rest. Does it make sense?
Oh, yeah.
Good. Any more question?
Nope, this is really impressive.
Okay. This is very nice method. It's one of those things. There are not many problems that you can do with image charge, but those that you can do, it's interesting. That makes the situation super simple. Otherwise, it's very difficult to calculate all the surface charges. And then later on, you will see that. So this example is for the conductor. For dielectrics, there are similar methods that you can use. We will deal with that in chapter 4. And that's very interesting because for those cases, you have charge Q and a different negative charge, not necessarily negative Q here. And the balance of these two charges, the way they create electric potential, it creates it creates all these electric fields here. And I can tell you, my very first research project when I was master's student was looking at certain bacterial membranes and looking at the electric charge interactions of the ions and the membrane, okay? And if you have these lipid membranes, biological membranes, what happens is that you have different dielectric constants. So you need to calculate all these interactions of the polarization and whatnot. And the shortcut that we used was we use image charges. And we said for every ion on this side of the membrane, we can consider there's another ion on the other side. And using this method of image made the whole project a lot easier. And I can say that that was the only way we could do the project. Otherwise, it would have been impossible. Okay, so for certain cases, this method of image is very useful.
Professor, how did you guys like image that for your project?
It was a little more complicated than this because here we have the whole half surface is just one conductor. And if you have a membrane, you have two layers, okay? So what you have is a reflection of images, okay? I can tell you, it's like this. You have one image, and then you have another image. Then you have image of the image, because what happens is that you have two layers, okay? So you have infinite number of image charges on both sides. So you have reflection after reflection. But on the other hand, after each reflection, the amount of the charge, the value of the charge becomes smaller and smaller. So you can eventually write a sigma of a series, and that series does not diverge. That series converges. Okay, so mathematically it was long, but you can do that image charge over and over again to calculate potential.
Gotcha.
If you want, I can send you the paper. It was published in, I think, 2005.
Sure, yeah. I was new without reminding you.
Yeah. If you go to my lab webpage, there should be that's my very, very first publication in Physical Review E. Cool. So going back to this, so far we calculated the surface charge density, and it's interesting to look at the total charges on the surface as well. So to do that, what I want to do is that I want to clear all this potentials and this one as well. Okay, so what we need to do is this. I want to calculate Q, the total charge induced on the surface, and that needs to be the integral of sigma dA over the surface of the conductor. Okay, so because here you have x2 and y2, and that is technically distance from the projection of Q on the surface, what I want to do is that I want to move to a spherical coordinate and use this as r squared. Okay, and if I do that, and that also becomes sigma as a function of r, the whole integral becomes sigma r times dr, which is r dr d phi. Okay, so this is dA, and integration is from r equals 0 to r goes to infinity. Okay, so for this integral, I'm gonna put the constants out of the integral. Q is a constant, D is a constant, 2 pi is a constant, so negative Q D over 2 pi. And here the integral of d phi, the integrand is not dependent on the phi, so what I can do is that I can just integrate phi separately, and it goes from 0 to 2 pi. So I can just separate that d phi, and I'm gonna already say that the total value of this is just 2 pi, and times the integral of r dr, r squared plus d squared, 3/2. And this goes from 0 to infinity. And this, let me get rid of this as well. And the 2 pi cancels out with this 2 pi. We get negative QD. Let me write like this, negative QD times, the integral is 1 over square root of R2 D2 from 0 to infinity. Okay, and the whole thing is 1 over D, so at the end we get negative Q. Okay, so if we look at the total charges, induced charges on the surface, sigma dA, sigma is surface charge density, dA is the surface, is the element on the surface of the conductor. We integrated from 0 to infinity. That means we are covering the whole surface of the conductor, and the integrand, not that complicated, but a little bit of mathematics. At the end, the total charges on the surface of the conductor becomes negative Q. And that is interesting because Q is the amount of the charge we put here, and it looks like it attracts the same amount of negative charges all the way to the surface. Okay, of course, this negative Q is spread around here all the way to infinity, but the total amount of induced charges has the same magnitude as the Q. Sounds good? Is it interesting?
Professor, how do you know it was from 0 to 2 pi? I got completely lost on that.
So this is d phi, right? So this is the integration on the surface. You know, let me draw it in a 3 dimensions so that might be easier for you to imagine what's going on. So imagine this is the surface of the conductor. Of course, it extends all the way to infinity. And this is the charge Q you have. And this is the surface. Okay. So here dA is something like this. And this angle is R d phi. And this is dr. Okay. So integration over d phi goes around the whole circle, which is from 0 to 2 pi. Okay, we are covering the whole surface. Okay, so r goes from 0 to infinity, and d phi is 2 pi, 360 degrees. And this is what we have here. Okay, integral of d phi times this. The integrand sigma is not dependent on the phi, it's symmetric. So you can just separate the d phi component, and that becomes 2 pi. Clear?
Yeah, I get it now. I was reading it from the book as well, and I just realized that it's describing the circle.
Oh, okay. Good, thanks for asking. So this is the total charges that we have on the surface, becomes negative Q. Okay, so there are two more things that I want to calculate relatively easy. What is the force on this charge Q? That's one thing. And the other thing is that what is the energy of the whole system of this charge distribution? Okay, let's first guess what should be the force on the charge Q. So with the consideration that we can make an assumption that we have a point charge on the other side, what do you think in terms of the force that this charge Q is experiencing? So imagine you are this charge right here. What are you feeling? Are you feeling a conductor, or you are feeling there's a negative charge all the way right here? Or these two are the same?
Are they the same?
Those two are the same. So from the perspective of this charge Q, okay, the kind of electric field it's experiencing is exactly the same as the electric field it experiences if we have a charge of negative Q on the other side. Even though we have this conductor and surface charges and profile of the charge, induced charges, but the electric field that this charge sees and observes is exactly the same as the electric field created if we had a charge of negative Q on the other side and not having any conductor in between. Okay, so that's the electric field that's created here. And then any force is a function of electric field, right? So as soon as you know the electric field, the force on any charged particle on any point charge is just the charge times Q. Okay, so the force that its charge is experiencing is simply the force that it experiences if we have a charge of negative D here. And that force is Q the charge Q times the charge negative Q, because this is negative, times 4 pi epsilon 0 times distance to the power of 2, which is 2d squared. Okay, so simply 1 over 4 pi epsilon 0 Q2 over 4d squared, and of course with a negative sign, and that negative sign means the force is attraction. Okay, so you have this attraction, and that is exactly similar to the case that you have the charge of negative Q on the other side. That's the force. Okay, and the way to convince is that just look at the electric field, and that electric field is created here. We said the electric potential and electric field is the same as the electric field created by the charge negative Q on the other side. Forget about the conductors. Okay, so force is the same as that. How about the energy of the whole system of this charge and a conductor? Do you think it's the same as the energy of 2-point charges or different? Any guess? So let's look at the energy of 2-point charges separated by distance 2d. Okay, so let's consider this case. You have charge of Q, you have charge of negative Q. What is the energy of this setting? Remember, we said the energy of 2-point charges is 1/2 sigma Qi VRI, right? So here we have 2-point charges. The energy is 1/2 negative Q times potential of Q created here. So negative Q times Q over 4 pi epsilon 0 times 2d plus the second one is positive Q times potential of negative Q created here. So that becomes 4 pi epsilon 0 times 2d. Okay, and if you look, these two terms are exactly the same. We're going to look at half of that, and that is 1 over 4 pi epsilon 0 Q2 over 2d. Okay, so this is the energy of 2-point charges, right? So do you think the energy in this system is equal to the energy in this system? Following all the discussions we had about the forces and energy and electric potential? Here is a little bit of trick, okay? It may look exactly the same because we have all these fields and electric potential on the positive z side of the space, the same as here, okay? But the quick bit trick is here, the little bit of trick is here. So if you look at the field lines for this case, we have field lines extended from the positive z space to the negative z space, okay? So we are looking at a situation that we have electric fields covering the whole space, positive z and negative z combined, okay? And if you remember, the energy of any system, you could write that as an integral of epsilon 0 by 2 integral of E2 d tau over all space. Okay, so electric energy is something that is stored in electric field in the whole space. And now in this case that we have 2-point charges, the electric field covers the whole space, positive to negative, all the way to infinity. But if we have conductors, what we have is electric field only in positive z direction, okay? And the electric field is in positive z direction is exactly the same as this electric field. On the negative side here, we have electric field exactly symmetric to what we have on the positive z, but on the negative z, here we don't have any electric field, okay? So if we compare this one and distribution of the electric field compared to this one, what we get is that here we have half electric field compared to this, okay? So the energy of this system of the conductor and Q should be half of the energy of this system that we have Q and negative Q on both sides. So whatever energy we calculated here, right, half of this applies to the case of conductor and the charge Q, Okay, so at the end, the energy we have here, the W should be half of what we had over here. So I'm going to call that mu q q prime, half of the 2-point charge system, which becomes -1/4 pi epsilon 0 q2 over 4d. Okay, so in terms of the electric field distribution, everything is the same. But now, because we are looking at the energy, and energy is proportional to electric field magnitude over the whole space, just with the reasoning, we can say this setting has half the energy of this setting because it has half field lines compared to the other one. Is it clear? Okay, any questions so far?
So for the energy, you're dividing by 1/2
Let
again.
me increase the volume a little. I had to turn on the heater in my office. It's pretty cold here. Can you repeat again?
Yeah, so for the energy
Okay.
thing, I know the difference. You're dividing by 1/2 to carry out this difference.
Yes, this 1/2 is to carry out the difference between the two.
So they're only similar in both force and
They are similar in force because force is dependent on electric fields. They are similar in electric field on the positive z direction, but energy is something that we need to integrate over the whole space. Okay, and the space in this one is half of the space of the other one. Here, the space is only on the positive z.
okay, I understand that. Thank you.
So if there's no more question, I can look at the other image charge problem before moving on to separation of variables. We are moving a little slower than, as usual. I'm teaching a little slower than what I anticipate. Cool. So another image charge problem is interesting too is this. Imagine this is a sphere, this is a conductor, and this conductor is connected to ground. So on the surface of the conductor, we have V electric potential being equal to 0 all the time. Okay. And then we put one charge of Q. Okay, we put charge of Q at the distance A from the center of the conductor. And the question is, what is the electric field and electric potential in the whole space outside the conductor? Of course, inside the conductor, V is 0 and electric field is 0 as well. But outside, the question is, what is the electric field? Okay, so what is the electric potential? Okay, so if you want to solve it directly, it's going to be a very difficult problem, right? But the thing is that we can find an image charge sitting somewhere inside the conductor in a way that satisfies the boundary condition. Okay, so here the boundary condition that we have is that electric field should be 0 on the surface of the conductor, and that is where R, the radius, is equal to R. Here I'm using a spherical coordinates. Okay, so imagine R is the capital R is the radius of the sphere. So if we are on the surface, potential should be 0. If we are at infinity, if r goes to infinity, the potential should be 0 as well. Okay, so these are the two boundary conditions. And of course, any space outside of the conductor, electric potential should satisfy the Laplace's equation as well. Okay, so now here, the shortcut is that we can assume there is one charge, one point charge sitting at this position at distance v from the center of the sphere, and the charge is carrying this q prime. Okay, so let's forget about the conductor. The whole problem, let's reduce it to having two charges, q here outside and another charge q prime inside the conductor, sitting a distance d from the center of the sphere and carrying the charge q prime. Okay, the value of the charge q prime and the position of the q prime can be adjusted such that these two charges combined, q and q prime, create electric field, electric potential in a way that it's zero on the surface of the sphere all the time. Okay, we can do that, and then because we have 2-point charges, of course, the second boundary condition where electric field, electric potential should be 0 at infinity is always satisfied. Okay, so the magnitude of this charge and the position is important. This is not something you can really come up by thinking, but this image charge problem is relatively famous. We just test if it's correct or not. Q prime should be negative of R over A times Q. So Q prime is negative. So in terms of the sign of the charge is opposite to Q. In terms of the magnitude is not exactly negative. It's R over A times Q. R is the radius of the sphere. A is the distance of the Q to the center. So R is smaller than A. So Q prime has a smaller magnitude compared to Q. The position B, where it's sitting, is R squared over A. So this is somewhere inside the conductor. Okay. Now, if you look at the position, if you look at the electric potential V as a combination of these two, so V should be.
Professor, did you write V equals to 2? What did you write there? Yeah. Right
V
below
equals R squared times H.
V. Below the circle, you wrote V equals to 2?
No, this is a question mark. So this is what we are trying to calculate, right? V outside this sphere.
Okay.
So the V here, electric field is 1 over 4 pi epsilon 0, right? Q over, let's say distance from the Q is R plus Q prime over R prime. Okay, so if we go around the surface here, and if this is R, this distance becomes R prime, and the distance from the charge Q is R. Okay, so if you're right here, the distance from Q is R, the distance from Q prime is R prime, and R prime can be written in terms of the value of V and this angle theta. Right, so R is basically a square root of R squared plus A squared minus 2AR cosine theta. Okay, R prime is a square root of R squared plus B squared minus 2BR cosine of the same angle theta. Okay, so R and R prime, you can write them in terms of capital R, the radius of the sphere, A and B, A and B are where the Q and Q prime is sitting, and of course it's a function of the angle theta as well. Okay, so if you look at this, R prime and Q prime, of course, B and Q prime are also can be written in terms of R, Q, and A. Okay, so I'm not going to continue all the way to the end, but I'm going to tell you if you substitute R and R prime here and Q prime from this, you will see the two terms in the bracket cancel each other out when you are right on the surface of the conductor. Okay, so very interestingly, with this charge magnitude and with this position, with 2-point charges, you can create a situation that you get electric potential being zero right on the surface of the sphere. Okay, and that satisfies the first boundary condition. The second boundary condition is already satisfied because we have 2-point charges. And so with that setting, you can calculate electric potential everywhere in space just following this setting of with the consideration of you have 2-point charges. Okay, so calculating the two terms in bracket and showing the electric field becomes zero. I'm going to let you do that. Okay, just follow these and follow the Q prime and B, and it's a good practice for you. Okay, so with this setting, you can calculate electric potential. If you want, you can always look at the magnitude of the electric field on the surface, and that way you can also calculate the electric charge distribution on the surface as well. Okay, very similar way that we did this previously with the other conductors. Okay, sounds good. Is the concept clear here and is the approach is clear?
So all of this by using geometry.
Just by geometry, yes. If you have a sphere, you can assume that you have point charges sitting here at a specific location with a specific amount, and that can fix electric potential in a way that we want to satisfy boundary conditions. And then some of the image charge problems you might encounter is combination of having a sphere and surface and so on, or half surface or things like that. Okay, you will see some of them in the problems that I will assign for this chapter. Okay, but the basic condition that you can really use the image charge problem is when you have a conductor, it's either a surface or a sphere, and then you should come up with image charges that can satisfy the boundary conditions you have. Sounds good?
Yeah.
Yeah.
Okay, so with this, I don't want to go into more details of this. Okay, so I'm just giving it to you as an example of how you can find image charge for the sphere. And if there's no question, we can move on to the next topic, which is separation of variables. Sounds good? Okay, so let's move on. Let me clean the board. Oh, okay. Okay. So separation of variable, as I said, is a mathematical trick. Okay, image charge was more a physical, conceptual trick to find the solution of the Laplace equation with the boundary conditions. Separation of variable is a mathematical method that doesn't work all the time, but for many problems it works, and it works really beautifully. So the concept here is this. Imagine you want to calculate electric potential, and electric potential is a function of two variables, x and y. Okay, for simplicity, let's assume it's only a function of x and y. And what we do is that we make an assumption that v can be written in terms of multiplication of two functions, x and y, in a way that the x is only a function of one variable x and y is a function of one variable y. Okay, so you have a function, a scalar function v, which is function of two variables. You separate it into two functions. Okay, so can you do it for every possible function? No. There are a lot of functions that you cannot really separate the x part and y part. But there are many functions that you can actually do so. Okay, so the assumption for the separation of variable method is, let's decide we can do this, okay, and see if it works or not, okay? And this is a very popular method because it actually does work for many different situations, okay? Once you separate these two, then Laplace's equation becomes interesting, because if you look at the Laplace's equation, for instance, for the case that we have two variables, the equation is partial v over d x squared plus partial v2 over d y squared is 0. Okay. Now, if you look at this equation and let's separate x and y, see what we get. Okay. The second derivative of v is with respect to x. Y is only function of y. So if we take this derivative, y becomes a constant. So what we get is that we get y, the function that is only function of y, times the second derivative of x with respect to x. And because x is only a function of one variable, it becomes not partial, but regular derivative. So from the first one, we get y times dx over dx2. And for the second term, we get x of x times d2y over dy2, and that becomes 0. Okay, and now the next part, I want to divide all terms by y times x, because I know that's not 0. And if we do that, I get 1 over x d2x over dx2, which is becomes, plus second term, which is 1 over y, d2y over dy2, and that combination becomes 0. Okay, so this is the Laplace's equation if we separate x and y. And what we are getting here, one term 1 over x dx over x2, the other term 1 over y d2y over dy2. Okay, and is that interesting? If you think about it, that's very interesting. We have two terms here. One term is only function of x. There's no y dependence whatsoever in the first term. And the second term is only function of y. There's no x dependence. So we have two separate functions being functions of separate variables, one x and y. If you add them up, that becomes 0. Okay. There is no way you can have this condition unless each of them is equal to a constant, and the combination of those constants is 0. So this can only happen if the first term, let's say this is C1, and the second term is C2. C1 and C2 should be constants independent of x, independent of y, with the condition that C1 plus C2 must be 0. Okay, and if you think about that, that means this equation is not technically one equation. This is just two equations. The first one is 1 over x. d2x over dx2 should be equal to c1. And the second equation, 1 over y, d2 y over dy2 becomes c2. Okay, so this is a major progress, moving from the Laplace's equation, which is second order, not ordinary. We have partial derivatives, second order equation. And now we came up with two differential equations, which are ordinary second order equations. And these type of equation, most of the time, we have general solution for. So solving these two are not that complicated compared to this. Okay, these are second order differential equations that we have general solutions available for them. Okay, my office is really chilly, so I need to put on my sweatshirt actually. The heating and cooling system is amazing in this building. Okay, so with this one, okay, let's stop here. I want to start one example, okay, and then continue with that, because these kind of equations, you should really work with one example and see physically what's happening, okay? So the example I want to do is example 3.3. From the textbook, okay, where we have a situation that we have one slab and we are trying to find electric potential inside that. The boundary conditions are very well characterized, and what we have is a situation something like this. We have two slabs. Okay, and imagine this is y direction, this is x direction, and this is z direction. Potential on this plane on the top, which is at y equals a, the potential here is 0. Okay, this is a surface of the conductor that potential is set at 0. On the bottom, this is at y equals 0, potential is 0 as well. On the surface on the left-hand side, at x equals 0, okay, this surface that x is 0, the potential is V0 as a function of y. So the potential is specified on this surface, but it's not necessarily constant. It's V0 y. On the surface on the top at y equals 0, potential is 0. At the surface at y equals 0, the potential is 0 as well. And the question is, what is the electric potential inside this slab? Okay, sorry. This is the question. What is the electric potential here? Okay, so this is the situation that we can really separate. The potential is going to be a function of x and y because of the symmetry that we have along the z direction. Okay, so we can separate x and y and only use two parameters, and we can move all the way and use these two ordinary differential equation to find v. Okay, so I'm going to erase some of the parts here because the board is getting too messy. Okay, and I want to erase all of this. I'm just going to keep these two equations on the top. I'm going to say that V is x of x times y of y. And for x, we have the differential equation that 1 over x d2x dx2 is C1. And for the y, we have 1 over y d2y dy2 is C2. And with the condition that C1 plus C2 should be 0. Sounds good? So here we want to calculate V with the assumption that V is combination of XX and YX. Okay, so it's important to first clarify what boundary conditions we have. So at y equal 0, we have V equals 0. So boundary condition number 1. At y equals 0 everywhere, we have electric potential being 0. At y equal a, again, we have potential being 0. At when x goes to infinity, we are so far away from this potential and we are so close to the surfaces that potential is 0. So at x goes to infinity, potential is again 0. And the last one is on the surface here. At x equals 0, the potential should be V0y. Okay, so this is the only surface that potential is clarified being not equal to 0, this surface. Okay, sounds good? So is the problem clear? What situation we have in terms of the geometry, what potentials we have, and what we are trying to find? Okay, that's important. So it's important for you to feel comfortable with the geometry, what we have here, and then we can move on to mathematics part. Okay. So what I do is that because of the geometry, I want to assume that the C1 is a positive number. Okay, I want to assume that C1 is a positive number and C2 is a negative number. These two should have opposite signs. Right now, it's not clear why I'm making that assumption, but later on in a bit, you're gonna see why I made that assumption. So I want to say C1 is equal to K2, just to make sure it's a positive number, and I want to say that C2 is negative K2, okay? By choosing it K2 and negative K2, I'm already including the condition that C1 and C2 should be 0. Okay, so I chose one positive number here and opposite of that for the other. Okay, so the equation for x we have is going to be d2x over dx2 is k2x. And the equation we have for y is, so this is for x. For y, we have d2y over dy2 is k2y. Sounds good? And are these two familiar differential equations for you? You know the general solutions? The first one is exponential, the other one is sine, cosine. Okay, so following these, you can already say that x of x is equation something like this, e to the power of negative kx plus b to the power of positive kx. Okay, and y of y is c sine kx plus d cosine ky. C sine ky, D cosine ky. These are the general solutions for x and y differential equations, okay? And if v is x times y, you can already say that a general solution for v of xy so far is a to the power of e negative kx plus b times e to the power of positive kx times c sine ky plus d sine d cosine ky. Okay, and this is the solution that we came up from these two equations. And these two equations, if you follow back, trace back what we did, these two are definitely going to satisfy the Laplace's equation. Okay, so this combination of x times y is definitely going to satisfy Laplace's equation. Okay, how about the boundary conditions? Not yet, we haven't included boundary conditions yet. Okay, so what I want to do now, I want to say that these constants can be simplified based on the boundary conditions, and next Tuesday we're gonna move on to more details of this. Okay, so what we have here is that we have four constants. One, A, second B, C, and D. And we need to determine these constants based on the boundary condition. And by the way, there are some conditions on K as well. Okay, so I'm gonna look into that later on. Okay, so things can be simplified first by looking at the boundary condition. Okay, so I'm gonna first look at the boundary condition number 3 that says at x at infinity, v must be 0. Okay, now if you look at this equation, we have x dependence here. This is an exponential of minus kx, and this is exponential of positive kx. This term, v times e to the positive kx, goes to infinity when x goes to infinity. This is not what we like. We want to see the potential going to 0 when x goes to infinity. And that means the constants b must be 0 because of the boundary condition 3. So I'm going to write 3 here. Okay, because of this boundary condition, b must be 0. And another thing, at y equals 0, the potential is 0, right? At y equal a, again, the potential is 0 as well. Okay, so we have two functions here, sine ky and d times cosine ky. Okay, so at y equals 0, if you want to have the potential being 0, the sine ky already meets that condition. Sine of 0 is always 0. What about cosine of ky? At 0, it becomes cosine of 0, and that is 1. Okay, we don't like that. We want a condition that it becomes 0 at y equals 0. So d must be 0 as well because of the boundary condition number 1. Okay, so out of the 4 constants, we already got rid of 2 of them, and we have just one, a to the e negative kx times c ky. Okay, so what I'm going to do next week is that I'm going to start from here and include more boundary condition and come up with more specific solution for this following. Okay, so we are out of time. I'm going to stop here. If you have any question, you can ask. And if not, then I'm going to stop session and we continue on Tuesday. Sounds good? Any question?
Yes, I want to know, can you go over again on the fourth boundary condition?
Which one? This one or this one?
No, on the fourth boundary condition, how x equals
Fourth boundary condition, this one?
Yeah.
So at x equals 0, this is what problem is. At x equals 0 on the surface here that they shaded, v is v0, y is just a specified boundary condition. It has certain potential non-zero. Okay. What is the shape of this? We don't know. It's just given like this. We just know it's non-zero. Sounds good?
Yeah, this is problem 3.3, right?
Example 3.2, yes.
Okay, thank you.
Okay, good. Any more question? So if not, I'm gonna stop here, and on Tuesday, I'm gonna continue this, okay?
Thank you, Professor.
Okay, good. You guys have a nice day and see you on Tuesday.
You too, Professor. Thank you.